Homo sapiens, who are we? Where did we come from? What is the nature of life itself? Questions a reflective mind might ask. But are these questions which we can really answer? Do we have enough of the pieces of this grand puzzle to even begin putting it together? Let's take a look. The first and most important puzzle piece was set in place in 1859 with the publication of Charles Darwin's On the Origin of Species, the seminal work in evolutionary biology. Darwin's opus laid out the framework for biological evolution with the concept that all life changes over time as a result of natural environmental pressures. This concept is fundamental to any attempt to answer the question, who are we? Other pieces of the puzzle have been provided by important fieldwork in the discipline of paleoanthropology, the study of ancient humans and their ancestral relatives in the fossil record. From the discovery of the bones of a Neanderthal in 1856 in Germany, to Raymond Dart's discovery of the Tong child, a juvenile Australopithecine, in 1924 in South Africa, to many other discoveries in Africa and around the world, the nature of human evolution is starting to come to light. The advent of modern genetics, especially evolutionary genetics, has led to not only great advances in our basic understanding of the fundamental mechanisms of evolution, but to insights into a basic timeline of human evolution, one of the most fundamental steps in answering the questions of who we are and where we came from. Now we have the tools to begin our attempt to answer our initial questions. Who are we and where did we come from? These tools being, 1, the concept of evolution, that life changes over time; 2, the results from field work and excavations in paleoanthropology; 3, the results from field work and studies in evolutionary genetics; and we will add one more, anthropological fieldwork related to the living examples of humankind that may shed light on our immediate human ancestors. And it is with this tool we will begin our quest to answer questions on the nature of humankind. Any great quest needs its set of clues. As our quest begins, anthropology provides us with our first clue, the San Bushmen of the Kalahari Desert of southern Africa. But why the San Bushmen? The first Homo sapiens lived in hunter-gatherer societies. The San Bushmen represent one of the best living examples of a hunter-gatherer society. Anthropological studies among the San Bushmen have led to great insights into what our hunter-gatherer past may have been like. The San people are magnificently adapted to living in an unforgiving environment. Over thousands of years as a hunter-gatherer society, they have gained an intimate knowledge of the plants and animals on which they depend for survival. The San people are intrinsically bound to the land in which they live. When we study the San Bushmen, we study what it was to be human many thousands of years in the past prior to the advent of agriculture. The San people are not only ancient in lifestyle, but also genetically. Detailed analysis of San DNA sequences has found that the San Bushmen are the most genetically diverse of any living human population. This genetic diversity is an indicator that they are the closest living representative to our Homo sapiens ancestral roots. Another indicator of the ancient lineage of the San Bushmen is their language. The click language of the Bushmen is thought to reflect characteristics of the first human languages. A past study by scientists at Stanford University theorized that the clicks found in some 30 African languages may harken back 40,000 years or more into the past. Thus, the language of the San Bushmen may represent one of the oldest languages still in use anywhere in the world. So we have our first clue, the San Bushmen, living in Africa, living in a hunter-gatherer society, and genetically speaking, the most ancient lineage of living human populations, speaking a click language that harkens back to the earliest human languages. An important first clue, one that emphasizes the important role Africa will play in our quest to find out who we are. Now we will take a look at the next clue in our quest. For this clue we will turn to paleoanthropology. Here we will dig ever deeper into the past as we continue our quest to find out who we are. In our quest to discover the nature of who we are, we will look for our second clue in paleoanthropology, the study of our ancient human ancestors in the fossil record. Hassan Bushman, our first clue, with the help of anthropology and genetics, has let us look some thousands of years back into our past. With the help of paleoanthropology, we will attempt to look millions of years into our ancient past. But looking millions of years into the past is not easy. If you've ever tried to investigate your own family's history, you know that going past your great-grandfather can be difficult, and that is only 3 or 4 generations. With paleoanthropology, we will be attempting to look anywhere from 20,000 to 160,000 generations back, and to really push it, possibly 280,000 generations into our past. Quite a stretch up the family tree. So to simplify the process of covering so much time and data, let's first acquaint ourselves with our relatives on our family tree. Homo sapiens extend from the present back to around 200,000 years in the past. There's a bit more to it than that, but we will cover that issue when we arrive at a future clue in our quest. Next on our family tree, we will place our cousin Homo neanderthalensis. Recent genetic evidence indicates some interbreeding between Homo sapiens and Homo neanderthalensis, but appears to have had little impact on the general genetic makeup of Homo sapiens. Homo neanderthalensis lived from approximately 30,000 years to 300,000 years into the past. Next, we will list Homo heidelbergensis, an extinct member of the genus Homo, which is thought to have lived from about 300,000 to 800,000 years in the past. Homo heidelbergensis is thought to have been the progenitor to Homo neanderthalensis and Homo sapiens. Farther up the family tree, we find Homo erectus. Homo erectus, also known as Homo ergaster in Africa, is thought to have lived over a range of time extending 70,000 years in the past to 1.9 million years in the past. Homo erectus is the first member of the genus Homo to migrate out of Africa. Fossil evidence of Homo erectus has been found in Africa and as far east as China. Next, we have Homo habilis. Homo habilis lived from about 1.4 million years in the past to 2.5 million years in the past. Homo habilis is considered to be one of the earliest members of the genus Homo and also thought to be one of the first stone tool makers. Moving ever farther into the past and up the family tree, we come to Australopithecus africanus. Australopithecus africanus lived between 2 and 3 million years into the past. Next we have Australopithecus afarensis. Australopithecus afarensis lived from about 2.9 million years ago to 3.8 million years ago. The best known example of afarensis is the famous 3.2 million year old fossil known as Lucy, discovered at Hadar, Ethiopia in 1974. Moving ever farther back into the dim past, we arrive at Auroran tungenensis, who lived between 5.6 and 6.2 million years into the past. Fossils of Auroran were discovered in the Tungan Hills of Kenya. Auroran may represent one of the earliest bipedal hominins. Next we have Sahelanthropus chadensis. Sahelanthropus chadensis is thought to have lived between 6 million and 7 million years in the past. Sahelanthropus represents one of the oldest members on the family tree Homo. There is some evidence based on the foramen magnum, the opening at the base of the skull where the spinal cord connects, that suggests Sahelanthropus may have walked upright. But due to the limited nature of fossil evidence surrounding Sahelanthropus, little is known about its true nature. With Sahelanthropus, we have come as far back into our past as paleoanthropology can take us. Genetic evidence based on DNA sequencing and molecular clocks puts the human-chimpanzee genome split at between 6 and 7 million years into the past. To go any deeper, we would have to enter into an area so speculative as to be of little use. So we will end our look at our family tree here and move on to a closer inspection of the fossil evidence. Homo Sapiens, who are we? Where did we come from? We begin Chapter 2 in our quest with a continued look into paleoanthropology and the fossil record of our ancient ancestors. Fossils of our ancient ancestors are very rare. It can take many years of arduous searching to find a single fossil. But where do we even begin to search? Let's take a look at the areas where paleoanthropologists have had the greatest success in discovering clues into our past. We will use the ancestral range of the San Bushmen as a starting point. The San Bushmen represent a living link back to our ancestral past. Let's see how that ancestral range matches up to the fossil record. East Africa, especially the Great Rift Valley, has played a central role in human evolution. The ancestral range of the San Bushmen is centered on this key geographic area. As we begin our look at the fossil record, we will see that the Great Rift Valley has been an important player in the story of our quest to understand the human fossil record. We will be concentrating on fossil sites in 5 African countries: Ethiopia, Kenya, Tanzania, South Africa, and Chad. Some of the most important fossil finds related to our human ancestors have been discovered in these countries. To find a fossil from, say, 3.5 million years in the past, you need to know where to look. But how does one know where to look? A key part of the answer is geology. Geology is the study of the Earth's physical structure and substance. Geologists are able to date rock layers and fossils by various methods. Radiometric dating is one of the most important methods. Radiometric dating uses the decay of natural occurring radioactive elements to date a rock sample or fossil. This is referred to as absolute dating or calendar dating because it provides an actual time range for the age of a sample. Another method of geological dating is stratigraphic dating, which is a relative dating method. It uses the principle that younger layers of rocks will lay atop older layers of rock. By combining these two methods with other geologic and archaeological methods, scientists are able to date rock layers and the fossils found in these layers. These methods enable paleoanthropologists not only to date fossils, but also point to rock layers where fossils of a certain age may be found. All of this field work and dating of rock layers has led geologists to arrive at a geological timescale for the Earth. Let's take a moment to familiarize ourselves with this timescale, as it will give us a reference for our continued quest to look into the fossil record of our human ancestors. The age of the Earth is calculated to be about 4.5 billion years old. This 4.5 billion year history can be divided into 2 broad stretches of time called the Precambrian and the Phanerozoic. The Precambrian stretches from 4.5 billion years ago to approximately 545 million years ago. The Phanerozoic begins 545 million years ago. It is marked by the large-scale appearance of multicellular life forms in the fossil record and marks the beginning of an expansive growth in Earth's biodiversity. The Phanerozoic is divided into 11 periods: the Cambrian, Ordovician, Silurian, Devonian, Carboniferous, Permian, Triassic, Jurassic, Cretaceous, Tertiary, and Quaternary periods. Let's start to look at the fossils of our human ancestors with a trip to the Jurab Desert of Chad, where fossils of one of our most ancient ancestors has been found. The Jurab Desert is located in northwestern Chad in northern Africa. It is part of the Great Saharan Desert System. The specific area where our potential ancestors' fossils were discovered is called the Taurus Manala Fossil Area. In 2001, members of the Franco-Chadian Paleoanthropological Mission led by Michel Brunet, working in the Taurus Manala region, discovered hominin fossils of a new species which they called Sahelanthropus chadensis. The fossils were dated at between 6 and 7 million years old. These are the oldest known fossils of a potential ancient human ancestor. The date of 6 to 7 million years puts the fossils in the same time range as the theorized genetic split between the Homo lineage and the chimpanzee lineage. Because of this, there is some debate among paleoanthropologists as to exactly what role Sahelanthropus plays in the family tree Homo. Is it a direct ancestor to Homo, or does it represent some parallel species to our ancient ancestor? Only future research will resolve this question. The current view of Sahelanthropus is that it probably walked upright, it had the brain size of a chimpanzee, and was probably about the same size as a chimpanzee. Fossils of other creatures found in the same strata include elephants, antelopes, hippos, crocodiles, hyenas, snakes, turtles, and fish. This leads paleoanthropologists to believe Sahelanthropus lived in an area of wooded savanna with lakes or rivers present. To find an equivalent environment today, we might look at Lake Chad, which lies on the border between Cameroon and Chad. The area around Lake Chad may be representative of the environment in which Sahelanthropus lived over 6 million years in the past. We took a look at the geological timescale a few minutes back. The last two periods of the timescale were the Tertiary and Quaternary periods. These cover the last 65 million years of Earth's history. The geologic boundary between the Tertiary and the older Cretaceous layer is known as the KT boundary. This is dated at about 65 million years ago. This layer marks the theorized asteroid strike that ended the reign of dinosaurs and began the rise of mammals. Bad for dinosaurs, but good for the family tree Homo. The Tertiary and Quaternary periods are divided into smaller time periods called epochs. The Tertiary breaks down into the Paleocene, Eocene, Oligocene, Miocene, and Pliocene epochs. We would find Sahelanthropus in the late Miocene epoch. Quaternary breaks down into the Pleistocene and Holocene epochs. We will be concentrating on the late Miocene epoch to the end of the Pleistocene epoch as we continue our quest to understand the family tree Homo. Our quest now takes us to Eastern Africa. We will visit the Tugen Hills in the Baringo district of western Kenya. The Tugen Hills are part of the Great Rift Valley system of Eastern Africa. In October of 2000, members of the Kenya paleontology team led by paleoanthropologists Martin Pickford and Brigitte Sanu discovered fossils of a new hominid species which they called Auroran tugenensis. The fossil specimens found so far belong to at least 5 individuals. The fossils are dated between 5.7 million and 6 million years in the past. This puts Auroran in the late Miocene epoch. The fossils were found in the Lacino Formation of the Tugen Hills. The fossils were dated using radiometric dating, magnetostratigraphy, and biochronology. The dating of Auroran tugenensis to around 6 million years in the past puts it in the time frame of the theorized human-chimpanzee genome split. Just as with Sahelanthropus, there is some controversy as to whether Auroran is a direct ancestor to modern humans or a distant relative. Fossil evidence indicates that Auroran was about the same size as a modern chimpanzee. There is evidence from the morphology of the fossil femur of Auroran that indicate it may have walked upright. Upper limb fossils of Auroran indicate that it was likely adapted to a life in the trees. Auroran may represent a transitional species adapting from a life in the trees to one more terrestrial in nature. Future research and discovery will hopefully clarify the questions surrounding Auroran. Fossil evidence found in conjunction with Auroran indicate that it probably lived in a marginal forest environment near a lake or stream. Fossils of animals found in the same strata as Auroran include impalas, leaf monkeys, colobus monkeys, fruit bats, tree hyraxes, and water chevrotains. These are indicative of a forested environment. Based on fossil evidence, it is theorized that one specimen of Auroran was stalked and killed by a large feline. The carcass was carried up into a tree to be eaten. The bones of Auroran dropped down into a body of water where they settled. Over time, the bones fossilized and came to rest in the Lacino Formation, where they lay until discovered 6 million years later. We will end Chapter 2 of our quest here. In Chapter 3, we will continue to seek answers into the nature of our ancient ancestors with the help of paleoanthropology. Homo Sapiens, who are we? Where did we come from? In the last chapter, we took a look at Sahelanthropus chadensis and Aurorantuganensis. In Chapter 3, we will continue our quest to learn more about our ancient ancestors through paleoanthropology. But before we resume our quest, let's digress. Let's take a moment to look at the actual mechanisms of evolution. How do living creatures evolve? Why do they evolve? These questions are fundamental to understanding the nature of life. Not only do these questions apply to life, but to the very nature of the universe itself. From the moment of the Big Bang, some 14 billion years in the past, there seems to be one immutable law to which nothing is immune. All things must change. Nothing stands still. The very fabric of space-time is expanding. Our universe expands and evolves. Galaxies evolve, stars evolve, star systems evolve, forming planets and bodies constantly in collision. Planets evolve in this chaotic environment, bombarded by smaller bodies as they are stressed by radiation and gravity. Our Earth revolves around the Sun, creating changing seasons. The Earth spins on its axis with a slow precession that impacts climate over thousands of years. The tectonic plates of the Earth inch almost imperceptibly, gliding over the Earth's molten mantle like giant conveyor belts. Along the boundaries of these tectonic plates, we find regions of mountain building and subduction where earthquakes caused by friction between the plates rattle the Earth, and volcanoes can erupt in cataclysmic fashion, affecting life for thousands of miles in all directions. Beneath the oceans, we find thermal vents along the boundaries of the tectonic plates, which give rise to colonies of life that derive their sustenance from chemosynthetic bacteria, just as creatures on the surface of the Earth are dependent on photosynthetic life for sustenance. This incremental changing of the Earth impacts life. Over eons, mountains arise only to be worn down. Oceans and lakes form and disappear. Forests arise and die. Once fertile, vibrant landscapes become desolate deserts. These changing landscapes impact weather patterns and climate. This slow, inexorable change impacts life in all its forms. Life either adapts or goes extinct. Natural selection in action. But by what mechanism does life change and adapt? The answer is basically DNA, deoxyribonucleic acid, a molecule that functions as an information handling system for creating life. We can think of DNA as being akin to a computer code. Binary computer code uses a series of zeros and ones to store information and allows computers to boot up and perform all kinds of marvelous functions using vast arrays of these two numbers. Similarly, DNA uses 4 nucleotides to encode the information for creating and sustaining life. Adenine, thymine, guanine, and cytosine. All known life forms on Earth are coded for using varying combinations of these 4 nucleotides. DNA is extremely proficient at storing and encoding information. If it wasn't, life would be pretty messy. But every so often, a mistake creeps into the system. We would label this mistake a mutation. These encoding mistakes or mutations can be beneficial, harmful, or have no impact at all on an organism. During the process of sexual conception, a new organism is formed from the mixing of the DNA of its parents, half from the mother and half from the father. This mixing results in a new organism which is unique at some level but still very much like its parents. This continuous mixing of DNA with the possibility of a mutation creeping into the process makes life very dynamic. But no matter how dynamic this process is, once the individual organism is conceived, its genetics are set. It can't change. To understand evolution clearly, we must think in terms of a population of organisms. To make an analogy, let's think of organisms as expressions of a collective pool of DNA or a gene pool. This gene pool is constantly changing and evolving through the mixing and mutating of DNA. The gene pool thus represents a range of possibilities and characteristics which are reflected in the individuals. Some individuals may be a bit bigger than the norm, some smaller, some faster, some slower, some smarter, some not so smart, some with sharp vision, some not. Some mothers very protective of their young, some not. A range of possibilities. Under optimal conditions, they may all thrive. But what if something changes? The forest you live in begins to thin out. The distance between trees becomes greater. Water resources become farther away. Protective cover becomes harder to find. The predator that stalks you now has more time to run you down. From the standpoint of the gene pool, if you are a little faster than your buddy, you survive while he or she is eaten. That individual no longer contributes to the gene pool, whereas you continue and your genes stay in the pool. Over many generations, this constant pressure on the gene pool will likely lead to a population of faster and more agile organisms, or smarter, or more cautious. As a consequence, the population of your predator may adapt by becoming faster and more agile or smarter. So evolution goes. Those organisms best suited to withstand the environmental pressures will be those that make up the gene pool and thus pass on their genes to the generations to come. Now take this a step further. Events occur in the environment which split the gene pool. A river grows wider and the populations on each side no longer mix. We now have two separate gene pools which undergo change and mutation isolated from each other. The two gene pools drift apart. The organisms as expressions of the gene pool begin to take on new characteristics. Given enough time and separation, the genetic distance between the two gene pools may be such that new species are formed. This is essentially how evolution works. A dynamic gene pool is encoded for by DNA. This DNA is constantly mixing, occasionally mutating while being selectively culled by natural environmental pressures. Out of this dynamic mix arise organisms best suited for the conditions at hand. Thus Mother Nature, not through design, not through foresight, but by carefully rubbing and blowing on her dice, plays her magnificent game of chance, and we and all we see are the result. A bit of skill and a bit of luck tempered and honed by the laws of chemistry and physics. We are not here because Mother Nature is a designer. We are here because Mother Nature is a gambler. Returning to paleoanthropology, we will continue our quest to learn more about our ancient ancestors on the family tree Homo. In Chapter 2, we looked at Sahelanthropus and Auroran, which took us some 6 million years back into the past. As we move forward in time, leaving the Miocene epoch and entering the Pliocene epoch at about 5.3 million years in the past, we begin to enter a more fossil-rich area of paleoanthropology. The family tree Homo begins to get a bit more crowded. Let's take a moment to look at our family tree. Sahelanthropus and Auroran are two early ancestral possibilities which lie in the time frame of the theorized genetic split between the lineages of Homo and chimpanzee, this occurring around 6 million years in the past. As we move forward in time, we find Ardipithecus cadaba at around 5.6 million years in the past. At around 4.4 million years in the past, we find Ardipithecus ramidus. These members of the genus Ardipithecus occur after the genetic split between the lineages of Homo and chimpanzee. What role Ardipithecus plays on the family tree Homo is still being researched. Moving forward to around 4 million years in the past, we come to the genus Australopithecus. The Australopithecines represent an important group on the family tree Homo. Included in this important genus, we find Australopithecus anamensis, Australopithecus afarensis, and Australopithecus africanus. The Australopithecines may have given rise to the genus Homo, but the exact role is still being debated. When we come to around 2.5 million years in the past, we find the first member of the genus Homo, Homo habilis. Homo habilis is the first human ancestor associated with stone tools. Around 1.8 million years in the past, we find Homo erectus, also known as Homo ergaster. Homo erectus represents a direct ancestor on the family tree. Homo erectus is the first member of the genus Homo to migrate out of Africa into Europe and Asia. Homo erectus gave rise to Homo heidelbergensis, who in turn gave rise to Homo neanderthalensis and Homo sapiens. As we look at our family tree, it is important to remember that we are dealing with dynamic populations that are slowly changing and adapting to variations in their environment over thousands and millions of years. The fossils that have been found represent but a small snapshot in time of a much greater and far more complex picture. There is always a desire to make the complex succinct so that it may be more easily grasped. But let's never lose sight of the fact that the tale of the family tree Homo is a very complex and multifaceted story. We will continue our quest to learn more about this amazing story in Chapter 4 with the help of paleoanthropology. Homo Sapiens, who are we? Where did we come from? In Chapter 4, we will continue our quest to learn more about the family tree Homo with the help of paleoanthropology. Traveling from 6 million years forward to 5 million years in the past, we will cross from the Miocene epoch into the Pliocene epoch. We will seek to illuminate the nature of some of our most ancient ancestors with a look at the fossil record. Our quest now takes us back to Eastern Africa. In Chapter 2, we looked at Sahelanthropus chadensis in Chad and Aurantuganensis in Kenya. We will now turn our attention to Ethiopia with a look at the genus Ardipithecus. Ardipithecus will take us from the late Miocene into the Pliocene epoch at 5.8 to 5.3 million years in the past. Let's continue our quest with a trip to the Middle Awash River Valley in northeastern Ethiopia in Africa. The Middle Awash River Valley is located in the Afar Depression, a geological feature which is part of the Great Rift Valley system of eastern Africa. In this dry, desolate desert region, paleoanthropologists have made some key discoveries which have helped to further illuminate our family tree. Between 1992 and 2002, a group of researchers led by Tim White of the University of California, Berkeley discovered fossils of an ancient hominin which they called Ardipithecus. Two species were found, Ardipithecus ramidus and Ardipithecus kadaba. Ardipithecus kadaba lived around 5.6 million years in the past. Ardipithecus ramidus lived around 4.4 million years in the past. Ardipithecus kadaba is an important ancient ancestor because it appears in the time frame of the human-chimpanzee genome split. Somewhere between 7 million years ago and 5 million years ago, we would find the last common ancestor of the chimpanzee line and the line of our human ancestor. Recent genetic research points to the genome split between chimpanzee and our human ancestor occurring around 6.3 million years ago. This genetic research points to a second surprising conclusion. Around 5.3 million years ago, there was crossbreeding between the chimpanzee line and the line of our human ancestor. This crossbreeding led to the creation of a hybrid line that was genetically viable. This hybrid line gave rise to the line of our human ancestor. This second division in the genome of humans and chimpanzees left its mark on the genome of our human ancestors in the form of the female sex chromosome X, which is about 1.2 million years younger than our other chromosomes according to the evolutionary clock. What role Ardipithecus plays in the story of the human-chimpanzee genome split may be revealed in future research. The fossils of Ardipithecus kadaba consist largely of teeth, fragments of the lower jaw, pieces of the forearm, finger bones, a collarbone, and a toe bone. To the untrained eye, these fossils may seem to hold little of interest, but to a paleoanthropologist, they reveal insights into the lifestyle of one of our ancient ancestors. Teeth, in particular, can be very informative. They can give us information on diet and social adaptations. Finger bones can tell us about their hands and how they use them. Toe bones can tell us whether an animal is adapted for climbing or walking. From an appearance standpoint, Ardipithecus kadaba was about the same size as a modern chimpanzee. It probably walked upright part of the time, but was still an agile climber. It most likely lived in a forested environment with lakes or rivers nearby and swamp-like conditions present. Moving forward in time, we would find Ardipithecus ramidus at around 4.4 million years in the past. Ardipithecus ramidus displays characteristics that are transitional between chimpanzees and the later Australopithecines. The canines are smaller than chimpanzee, but larger than Australopithecines. Ardipithecus ramidus most likely lived in a forested environment near lakes and rivers. The genus Ardipithecus moves us farther down the family tree towards our own human beginnings. We will next look at the genus Australopithecus, which moves us ever closer to the beginning of our own genus, Homo. As we begin our look at the genus Australopithecus, let's review our journey so far. From 7 million years in the past to 5.7 million years in the past, we have looked at the potential human ancestors, Sahelanthropus and Auroran. With Ardipithecus cadaba at around 5.6 million years in the past, we begin to leave the Miocene epoch and move into the Pliocene epoch at 5.3 million years in the past. Ardipithecus ramidus moves us well into the Pliocene epoch at around 4.4 million years in the past. We begin to encounter Australopithecus at around 4.2 million years in the past. The Australopithecines are a very important relation on the family tree Homo. Let's begin our look at the genus Australopithecus on an October Saturday in 1924. It is October 11, 1924, a Saturday in Melrose, an upper-class area of Johannesburg, South Africa. Raymond Arthur Dart, the young director of anatomy at the University of Witwatersrand, is getting dressed for a wedding. He is the best man. His wife Dora is urging him to hurry. As he dresses, he looks out the window of his home to see two men from the South African Railway struggling up his drive with two wooden crates. It is the shipment of fossils from the Buxton Lime Quarry in Tong, South Africa that he has been expecting. Raymond's wife pleads for him to concentrate on the wedding, but as soon as she is off to get dressed, Raymond is out the door. He wrenches the top off of the first crate. It is full of cut limestone containing various fossils. Raymond is disappointed in the contents. He turns to the second crate and removes the lid. His eyes fall on an endocranial cast, a fossilized brain from the interior of a skull that he sees lying atop the contents. As he picks up the fossilized brain, Raymond can see right away that the brain is too large for a baboon or chimpanzee, yet too small to be that of a primitive man. He senses he is holding in his hands something new, something very different. He feverishly rummages through the crate to see if there is a face to fit with his brain. He finds a large rock into which the fossilized brain fits perfectly. In the rock, he can see hints of a skull. Raymond begins to realize he may have found one of the most significant discoveries in the history of anthropology. But the wedding is imminent. His friend Crystal Byers, the bridegroom, implores Raymond to get dressed. Reluctantly, Raymond stores his two new treasures in his wardrobe and prepares for the wedding. The next day, he begins the arduous task of delicately extracting the skull from the rock. On December 23, 1924, 73 days after beginning the task, the rock splits open, partially revealing the skull face. It is the face of a young 3-year-old hominid specimen that Dart will christen Australopithecus africanus, his Tong's baby as he affectionately called it. This specimen would be the beginning of proof that mankind had originated in Africa, a theory put forth by Charles Darwin. The prevailing view in the early 20th century was that mankind had originated in Eurasia due to discoveries of Neanderthal, Cro-Magnon, and Homo erectus fossils in Europe and Asia. Raymond Dart argued that Africa was the cradle of humankind. The debate continued for many years, but in the end, Raymond Dart and Charles Darwin were proven right. Africa was recognized as the birthplace of humankind. Let's begin our look at the genus Australopithecus with an overview of the fossil finds of Australopithecines in eastern Africa. Fossils of Australopithecus have been found in Ethiopia, Kenya, Tanzania, and South Africa. In the last few minutes, we looked at the discovery of the Tong child in South Africa by Raymond Dart. The Tong child is dated at 2.5 million years in the past. In 1974, Mary Leakey discovered fossils of Australopithecus afarensis in Tanzania, which dated to 3.8 million years in the past. In 1997, Maeve Leakey discovered fossils of Australopithecus anamensis in Kenya at Kanapoi, which dated to around 4 million years in the past. In 1974, Donald Johansen discovered fossils of Australopithecus afarensis in Ethiopia dated to around 3.2 million years in the past. Johansen christened his fossil find Lucy after the Beatles' song Lucy in the Sky with Diamonds. The genus Australopithecus covers a time span from around 4.2 million years in the past forward to around 2 million years in the past. The Australopithecines ranged all across eastern Africa from present-day Ethiopia to South Africa. The Australopithecines represent a key evolutionary link in our quest to discover the beginnings of Homo Sapiens. In Chapter 5, we will continue our look at the family tree Homo and the role played by the Australopithecines in this epic tale. Homo sapiens, who are we? Where did we come from? In Chapter 5, we will continue our look at our ancient ancestors on the family tree Homo with the help of paleoanthropology. In Chapter 4, we begin our look at the genus Australopithecus. In Chapter 5, we will delve deeper into the role Australopithecus plays on our family tree. Let's refresh our memory with an overview of the family tree Homo. In the past chapters, we have looked at Sahelanthropus, Auroran, and Ardipithecus. This brings us up to about 4.5 million years in the past. Australopithecus will take us from around the 4 million year mark to the 2 million year mark. Starting around 2.5 million years in the past, we will begin to encounter our ancestors in the genus Homo. Our own species, Homo Sapiens, will make an appearance around 200,000 years in the past. But before we begin our look at Australopithecus, let's take a moment to digress. Back in Chapter 3, we touched on some of the components driving the evolution of species. Let's take a moment to look at the climatic factors affecting the evolution of our ancestors in Eastern Africa. Across the millions of years of our Earth's history, one of the most important factors driving evolution has been the ever-changing surface of the Earth. Via plate tectonics and continental drift, the Earth itself is evolving. The movement of land masses causes changes in ocean currents, wind patterns, global temperatures, and climatic conditions over thousands and millions of years. Everyone is familiar with the look and appearance of our Earth today from maps, globes, and photos of our planet from space. But if we went back to the Permian period some 255 million years ago, we would find a very alien-looking Earth. All of the continental masses that exist today were grouped together into a supercontinent which we now call Pangaea. Slowly, over the eons, plate tectonics and continental drift reshaped our world. By 200 million years in the past, Pangaea had broken up into two continental groups which geologists call Laurasia and Gondwanaland. By the 150 million year mark, we would see land masses that could be recognized as precursors to the continents we know today. By the 65 million year mark, at the time of the asteroid strike that is theorized to have caused the demise of the dinosaurs, the Earth we know today was beginning to take shape. From 65 million years ago to the present, the surface of the Earth we recognize today took its form. But the tectonic plates of the Earth are still in motion. Millions of years in the future, the surface of the Earth will again be very different. As we noted earlier, this movement of land masses affects global climate. If we could visit our Earth 65 million years in the past, we would find a world that was warm with little temperature variation from the equator to the poles. But around the 50 million year mark, we would start to note a change. The Earth began to cool. The global climate overall became cooler with periods of rapid cooling at the 33 million year mark, the 15 million year mark, and the 3 million year mark. Three main factors are cited in this cooling trend. Number one, the collision of the Indian subcontinent with the Asian landmass, which resulted in the upthrusting of the Earth's crust, leading to the creation of the Himalaya Mountains and the Tibetan Plateau starting about 50 million years ago. Number two, changes in the topography of the North Atlantic Basin, which reduced the northward flow of warm surface water. Number three, the closing of the Tethys Sea by a land bridge that formed between the African and Eurasian continents. This land bridge blocked the connection which had existed between the Atlantic and Indian Oceans, reducing the area of tropical and subtropical oceans. The present-day Indian Ocean and the Mediterranean Sea are remnants of the ancient Tethys Sea. Of these three factors, the uplifting of the Tibetan Plateau may be the most important. In the late Miocene, around the 8 million year mark, there was considerable uplifting of the Tibetan Plateau by between 1 and 2.5 kilometers. This uplifting had a wide-ranging impact on the weather systems affecting Eastern Africa. A strong flow of warm, dry air from East Central Asia replaced the moist, low-level oceanic winds which had impacted the East African environment. The result was that Eastern Africa began to dry out. The climatic picture of Eastern Africa was further complicated by local faulting and uplifting of terrain in the Great Rift Valley. This led to a fractured and ever-changing environment which oscillated between periods of wet and dry over thousands of years. This dynamic environment eventually pushed our ancestors from a forested environment to one of wooded grasslands and open savannas. Our ancient ancestors evolved in a very dynamic environment. You could say that our DNA was forged in the fire of chaos. Out of this fire came a creature whose greatest attribute was that it was capable of dealing with change. More so than any creature that had existed prior, our ancestors were evolving the ability to overcome the changing environment through intelligence, social interdependence, and the harnessing of technology. We were becoming the ultimate survivor. With this in mind, let's return to our look at the genus Australopithecus. Let's see what role they played in this dynamic saga that led to the evolution of our genus, Homo. As we begin a more in-depth look at the genus Australopithecus, let's review some of the major points covered in Chapter 4 and earlier in this video. The genus Australopithecus ranged across eastern Africa over a period of 2 to 2.5 million years and possibly more. The geographical range appears to cover most of eastern Africa, with some fossil evidence indicating the possibility of westward extension of the range into Central Africa into present-day Chad. The three main species of Australopithecus recognized by paleoanthropologists are Australopithecus anamensis, Australopithecus afarensis, and Australopithecus africanus. Two other species of Australopithecus named are Australopithecus bar el Ghazali and Australopithecus sediba. Another group of Australopithecines, known as the robust Australopithecines, is thought to constitute a separate genus which has been given the name Paranthropus. The robust Australopithecines are thought to represent a different evolutionary line which did not contribute to the genus Homo, and therefore we will not cover them in this video. Fossils of Australopithecus anamensis have been dated to around 4.2 to 3.9 million years ago. The fossils, representing about 20 individuals, have been found in Kenya and Ethiopia. The first fossil of Australopithecus anamensis was found at Kanapoi near Lake Turkana in 1965 by Brian Patterson. The fossil was tentatively assigned to the genus Australopithecus at the time. It was not until 1995 that further research and discoveries in the Lake Turkana region led paleoanthropologist Meev Leakey to assign the 1965 fossil and other new discoveries to a new species christened Australopithecus anamensis. In 2006, new fossil remains of Australopithecus anamensis were found in the Middle Awash River Valley in Ethiopia by Dr. Tim White. These new anamensis fossils were discovered just 6 miles from the site of the discovery of fossils of Ardipithecus ramidus, which were dated to 4.4 million years ago. The fossils of Australopithecus anamensis were dated to 4.2 million years ago, thus representing a separation in time of about 200,000 years for these two relatives on our family tree. Fossils of other animal remains found at the Lake Turkana site indicate that Australopithecus anamensis lived in a transitional environment consisting of a mixture of woodland and grassland with rivers present. Fossil leg bones of anamensis seem to indicate that it was bipedal, that it walked upright on 2 legs. In general, the fossil record of Australopithecus anamensis is rather sparse. Hopefully, future field research will fill in the unknowns on anamensis and what role it plays on our family tree. Australopithecus anamensis shows characteristics which are transitional between Ardipithecus ramidus and Australopithecus afarensis. Some paleoanthropologists believe that anamensis should be classified with the Australopithecine species afarensis and should not be considered a separate species. Let's now take a look at Australopithecus afarensis and see what role afarensis plays on our family tree. Fossils of Australopithecus afarensis have been discovered in Ethiopia, Kenya, and Tanzania. The fossil remains have been dated from 3.9 to 2.7 million years in the past. The species of Australopithecus designated afarensis was first named in 1978 by Donald Johansen and Tim White following the study of fossils found in northeastern Ethiopia. The fossils Johansen and White were studying were those of one of the most widely publicized examples of Australopithecus afarensis ever found, the famous Australopithecine christened Lucy. The fossil remains of Lucy were discovered in November of 1974 by Donald Johansen and Tom Gray. The fossils were found in the Afar Triangle Middle Awash area near Hadar, Ethiopia. The fossils of Lucy were dated to 3.2 million years ago. This schematic of the soil layers gives a general idea of the stratigraphy of the site in which the fossils of Lucy were found. Potassium-argon dating of the volcanic layers in the formation were important in establishing the date of the fossils. The research team found several hundred bone fragments which represented about 40% of the entire skeleton of Lucy, one of the most complete Australopithecine skeletal remains ever found. It was estimated that Lucy stood about 3 feet 6 inches tall, or about 1.1 meters. She weighed in at around 65 pounds. Her appearance would have been somewhat chimpanzee-like, but her posture would have been more upright. Lucy's spine had a lumbar curve which indicates habitual bipedalism. She also had a valgus knee, which is a further indicator of walking upright. If we look at the pelvic bones of a chimpanzee, an Australopithecine, and a member of our own species, Homo Sapiens, we can see that the Australopithecine pelvic bones are much closer to that of Homo Sapiens than that of chimpanzees. The movement of Australopithecines was becoming more human-like and less chimpanzee-like. Environmental dynamics, coupled with natural selection, were driving our ancestors down a path of cascading change. Changes in locomotion would impact hand-eye coordination, which would impact brain size and intelligence, which would impact social structure and nurture bonding between males and females, which in turn impacted sexual selection. This complex and dynamic milieu was creating a biological feedback loop that was pushing our ancestors toward becoming human. In Chapter 6, we will continue our look at the genus Australopithecus and the role they play on the family tree Homo with the help of paleoanthropology. Homo sapiens. Who are we? Where do we come from? In Chapter 6, we will continue our quest to learn more about our ancient ancestors on the family tree Homo. Let's continue our look at the hominid species Australopithecus afarensis with the help of paleoanthropology. Our quest takes us back to Eastern Africa to Ethiopia. We will visit a place called Dakika in the Afar Triangle area near the Awash River. Dakika is just a few miles south of Hadar, Ethiopia, not far from where the fossils of the Australopithecine called Lucy were found in 1974. It was here in Dakika on December 10th of the year 2000 that Serezanai Alemseged and his research team discovered the remains of a young Australopithecus afarensis, which Serezanai named Salam. Over 60% of the entire skeleton of Salam was recovered. Salam is thought to have been a young female Australopithecine who died at the age of 3 years old. She may have drowned in a flood along the Awash River. Shortly after death, her body was probably buried under sand and gravel. This would account for the recovery of so much of the skeleton of Salam. The fossil remains of Salam are dated to about 3.3 million years in the past. This makes Salam approximately 120,000 years older than the Australopithecine called Lucy. The skeletal remains of Salam pose some interesting questions. Let's see what the fossils of Salam can tell us about the state of our evolution some 3.3 million years in the past. Because Salam died at approximately 3 years old, her skeletal remains may help give us insight into the ontogeny or the development and growth patterns of Australopithecus afarensis. The nearly complete skull and brain cast of Salam may shed light on the growth pattern of the Australopithecine brain. Salam's brain cast indicates that her brain was slightly smaller than that of a chimpanzee at the same age. As an adult, her brain would have been larger than a chimpanzee's brain. This could be indicative of Australopithecines having an extended brain development cycle as in Homo sapiens. This longer development cycle of the brain allows a more complex brain to form outside the womb. This may indicate that young Australopithecines needed an extended period of care and nurturing similar to childhood in humans. If we look at the brain growth cycle of a human and a chimpanzee, we would find that the chimpanzee brain attains about 50% of its size in the womb. The human brain only attains about 25% of its size while still in the womb. Thus, nearly 75% of a human's brain development occurs after birth. From birth to around age 5 or 6, a human brain grows to about 90% of its adult size. This extended childhood of Homo sapiens has been essential to our evolutionary success. It allows for complex cultural learning and interaction. During this extended growth cycle, the brain is bombarded by parental and environmental stimuli, which is crucial in acclimating the neophyte to the world in which it must live and survive. The question we have when looking at the brain development of our ancestors, such as Australopithecus afarensis, is whether they had already started down this path of increasing brain complexity. Salam seems to hint at this possibility, but only future research will help to answer this important question. Salam's remains also produced only the second hyoid bone ever recovered from one of our ancient ancestors. The hyoid bone is a tiny bone which attaches to the tongue muscles. In Salam, the hyoid bone is much more like a chimpanzee than a human. This can give us insight into Salam's vocalizations. It's likely that any sounds Salam made were more like a chimpanzee than a human. The structure of Salam's inner ear was closer to that of apes than humans. Since the inner ear plays a role in balance, this could indicate that, though Salam walked upright, she would not have been as agile and quick on her feet as members of the genus Homo. Salam's neck was short and thick, more like an ape than a human. The human neck, being slender and longer, helps stabilize the head when running. Salam's shorter neck may be an indicator that Australopithecines, while capable of walking upright, were not good long-distance runners. Salam's upper torso displays features that are adapted to tree climbing, such as long curved fingers. Salam is probably representative of a creature in transition from arboreal living to terrestrial living. Natural selection was pushing the adaptation of bipedalism, while the adaptation of the upper torso followed. At 3.3 million years in the past, our ancestors were transitioning from a forested habitat to one of wooded grasslands and open savannas. As eastern Africa began to dry out and change, our ancestors were adapting to that change. Salam represents a small snapshot in time of that transition. If we close our eyes, maybe we can imagine standing by a flood-swollen awash river some 3 million years in the past. Dark storm clouds boil across the African sky. Lightning dances, ramming darkness down gullies and ravines. Trees shudder and scream. Winds howl, raking the earth. Rain sizzles and explodes off the rock face. Suddenly, a flash of lightning reveals a small group. They struggle along the banks of the river. They are seeking shelter. A young 3-year-old clings to her mother. She is terrified by the storm. She screams out. The waters are rising so fast. The 3-year-old slips. Her mother lunges for her, but the strength of the water is so great. They are washed away. The mother manages to grasp a limb. She clings to it with all her strength. In the roar of the darkness, she hears the screams of her daughter fading and fading. We may never know the exact details of the last seconds of Salam's life, but through the efforts of paleoanthropologists such as Zarazani Alemseged, our ancient ancestors like Salam can help illuminate the nature of our own life and existence. Let's now continue our look at the genus Australopithecus with a journey to Tanzania in eastern Africa. We will travel to the site of Lutoli, which lies just 45 kilometers or about 28 miles south of the famous Olduvai Gorge. The site of Lutoli holds some of the most interesting finds associated with the genus Australopithecus. Surprisingly, no bones are involved. What the Lutoli site is famous for is its footprints. Approximately 3.6 million years ago, several of our hominid ancestors walked across an area of wet volcanic ash. They left behind a trail of footprints about 27 meters or 88 feet long. An eruption of the nearby volcano, now called Sodoman, had deposited a layer of volcanic ash across the countryside. Light rain had fallen on the ash layer, creating a sort of muddy cement. When our ancestors walked across the area some 3.6 million years ago, their footprints were captured in the wet ash layer. Subsequent eruptions of the volcano laid down further layers of ash which helped preserve the footprints. The footprints of numerous animals were also captured in the ash layer. Gradually, erosion wore down and exposed the layer of tracks. In 1976, paleoanthropologist Andrew Hill, a member of Mary Leakey's Lutoli research team, literally stumbled upon this rock layer while doing field work at Lutoli. Further work at the site in 1978 by Paul Abel uncovered the hominin footprints. The most striking thing about the footprints is how human-like they appear. The tracks seem to have been laid down by a heel-strike stride pattern just as humans walk today. The big toe is in alignment with the rest of the toes as in humans. In comparison, the big toe of a chimpanzee is angled approximately 45 degrees to the other toes. The close spacing of the footprints indicates a short stride, which could mean short legs. The varying size of the two sets of tracks also points to one individual being larger than the other. Several theories have been put forth over the years concerning the interpretation of the footprints since the tracks were first discovered. One of the earliest theories was that the tracks represented a male and female walking together in stride, side by side, with possibly a smaller individual following in the male's footsteps. Over the years, further study and more advanced techniques have revised the theory to two adult females walking one behind the other with a child following along on their left side. The actual sex of the individuals is speculative, but the tracks do seem to represent three individuals. The tracks have been designated G1, G2, and G3, with G1 being the trail of the smaller individual which left the most distinct impressions. Most paleoanthropologists theorize that the footprints were most likely made by members of the species Australopithecus afarensis. Fossils of Australopithecus afarensis have been found nearby in the same sediment layer. As no other concurrent hominin species has been found, this lends credence to Australopithecus afarensis being the track maker. This ancient trail of footprints seems to indicate that bipedalism was well established in our ancestors some 3.6 million years in the past. The fossils of Salam and Lucy seem to testify to what the Laetoli footprints reveal. Our ancestors in the genus Australopithecus afarensis were adapting to the changing environment in eastern Africa. Natural selection was pushing bipedalism in the lower body. The upper body was following as it adapted to the new dynamics created by bipedalism. Of these new dynamics, freeing of the hands may be the most important. With the hands free to take on new tasks, natural selection could push the upper body and the brain in new and more complex directions. On that day in the distant past, some 3.6 million years ago, as our ancestors walked across that stretch of muddy volcanic ash, leaving behind only their footprints, the earliest beginnings of our own genus Homo lay over 1 million years in the future. The beginning of our own species, Homo Sapiens, lay some 3.4 million years in the future. When we gaze at the footprints today and look back on that day some 3.6 million years gone by, we contemplate what our ancient ancestors must have been like. And if we thought about it, we might muse on the fact that we are the only species on the planet capable of that contemplation. In Chapter 7, we will continue our look at our ancestors in the genus Australopithecus and what role they played in the evolution of our own genus Homo with the help of paleoanthropology. Homo Sapiens. Who are we? Where do we come from? In Chapter 7, we will continue our look at the genus Australopithecus with the help of paleoanthropology. Before we continue, let's digress for a moment. We call ourselves Homo Sapiens. Where does this name come from? In general, it comes from the desire or the need of the human mind to quantify or categorize the world around us. Specifically, the term Homo sapiens arose out of the work of the Swedish botanist Carl Linnaeus, who popularized the use of binomial nomenclature in his book Systema Naturae and Species Plantarum, published in the 1750s. The work of Linnaeus helped lay the foundation for the scientific or biological classification of life on Earth. Back in Chapter 3, we touched on DNA and the mechanisms of evolution. Scientific or biological classification is a way of categorizing or mapping biological relationships resulting from the evolution of the massive DNA gene pool that is inclusive of all life on Earth. If we took a look at the biological classification of Homo sapiens, we might see something like this depending on the taxonomic system used. We are listed in the kingdom Animalia, being an animal as opposed to a plant, a fungi, a protozoan, or a bacteria. Our subkingdom is Eumetazoa, being a multicellular animal with differentiated tissue as opposed to the parazoa, such as sponges. Our phylum is Chordata, meaning we display a notochord in early development. In the case of Homo sapiens, in embryonic development. Our subphylum is Vertebrata, indicating we have a backbone or a spinal column. Our superclass is Tetrapoda, designating four-legged or four-limbed. Our class is Mammalia. We nurse our young via mammary glands. Our subclass is Steria. We give birth to live young without the need of a shelled egg. Our infraclass is Eutheria. We are placental animals as opposed to a marsupial. Our order is primates. We display a wide range of characteristics including stereoscopic vision and adaptation to climbing trees. Our suborder is Anthropoidea. We have stereoscopic color vision and large complex brains for our size. Our infraorder is Catarrhinae, meaning we have narrow down-facing nostrils and 32 teeth. Our superfamily is Hominoidea, which includes humans, chimpanzees, gorillas, orangutans, and gibbons. Our family is Hominidae, which includes humans, chimpanzees, gorillas, and orangutans. The members of this group would be called a hominid. Our subfamily is Homininae, which includes humans, chimpanzees, and gorillas. The members of this group would be called a hominine. Our tribe is Homininae, which includes humans, chimpanzees, and all of the fossil ancestors of the genus Homo, such as Sahelanthropus, Auroran, Ardipithecus, Australopithecus, and all of the extinct members of the genus Homo, such as Erectus and Neanderthalensis. The members of this group would be called a hominin. This brings us to our own genus Homo and our own species Sapiens, and to go a step further, our own subspecies Sapiens, which differentiates us from more archaic forms of Homo sapiens. For example, Neanderthals would be classified Homo sapiens neanderthalensis, and we would be Homo sapiens sapiens. If we look at this graphic overview covering the last 15 million years of our evolution, we note around the 14 million year mark, the human, chimpanzee, gorilla line and the orangutan line were undergoing speciation or a genetic split. Speciation occurs gradually over many thousands of years as a gene pool becomes divided. This division most likely arises out of geographic separation, but other factors may also play a role. Around or before the 8 million year mark, another speciation occurred, leading to the genetic split of the human-chimpanzee line from the gorilla line. This was reflected in the taxonomy, which places humans and chimpanzees in the tribe Homininae and the gorillas in the tribe Gorillinae. And as we've covered in past chapters, between 7 million and 5 million years ago, the human-chimpanzee line underwent speciation, which led to the genetic split between the line of Homo sapiens and the chimpanzee line. The chimpanzee line underwent speciation around the 1 million year mark, leading to the creation of the species Pan troglodytes and Pan paniscus. Approximately 30,000 years ago, our closest remaining relative on the family tree Homo, Homo neanderthalensis, faded from existence, leaving us the sole living member of the genus Homo. Let's now return to our look at the genus Australopithecus with a trip to South Africa. Back in Chapter 4, we took a look at the discovery of the first fossils of Australopithecus africanus in South Africa in 1924 by Raymond Dart. Fossils of Australopithecus africanus have been discovered at only 4 sites in South Africa. These sites are Tong in 1924, Sterkfontein in 1934, Makapansgat in 1948, and Gladysvale in 1992. Before starting a detailed look at Africanus, let's take a moment for a quick overview of the genus Australopithecus. In past chapters, we have looked at Australopithecus anamensis in Ethiopia and Kenya. Anamensis lived from about 4.2 to 3.8 million years ago. We looked at Australopithecus afarensis in Ethiopia, Kenya, and Tanzania. Afarensis lived from about 3.8 to 3 million years ago. The species Australopithecus africanus has only been found in South Africa. Africanus lived from about 3 to 2 million years ago. Let's also mention the species Australopithecus Bar el Ghazali. The fossil find of Bar el Ghazali consists of a jaw fragment and about 7 teeth. It was discovered in 1993 by Michel Brenet near Koro Toro in Chad. The fossil dates to about 3.6 million years ago. The most interesting aspect of this fossil find is that it is located about 2,500 kilometers west of the Great Rift Valley. This seems to expand the range of Australopithecus well into Central Africa. Though assigned to the new species Bar el Ghazali, some paleoanthropologists believe it is more rightly assigned to the species Afarensis, as it falls in the same time range and within the variation parameters of the species Afarensis. Putting all of this together, we find the genus Australopithecus living over a span of about 2.2 million years or more, ranging across eastern Africa, possibly into north central Africa. The time range of Australopithecus is from about 4.2 million years ago to around 2 million years ago. Around the 2.5 million year mark, we would find the first representative of the genus Homo, Homo habilis. This gives us about 500,000 years of overlap between Australopithecus africanus and Homo habilis. What role did Australopithecus africanus play in the evolutionary transition to the genus Homo? Let's see what the fossil remains of Australopithecus africanus can tell us. On April 18, 1947, Dr. Robert Broom and John T. Robinson were doing excavation work at the Sterkfontein site about 70 kilometers southwest of Pretoria, South Africa. Their efforts on this day produced the most complete skull of Australopithecus africanus ever found. Initially, the skull was assigned the binomial name Plesianthropus transvalensis, from which it got the nickname Mrs. Please. The classification of the fossil was later revised to the species Australopithecus africanus. The fossil skull of Mrs. Please has been dated to between 2.2 and 2 million years old. Originally, the skull was thought to belong to an adult female Australopithecine, but more recent studies seem to indicate that it was a subadult Australopithecine, possibly even a male. In August of 1947, Dr. Broom discovered another set of fossils at Sterkfontein, which included the pelvic bone from an Australopithecus africanus, which was strikingly human-like in appearance. This fossilized pelvic bone was one of the first discoveries to clearly demonstrate the bipedality of Australopithecus africanus. In Australopithecus africanus, we find a creature transitioning toward Homo-like characteristics, but still retaining ape-like aspects. It was bipedal, but probably not with the agility or facility of modern humans. Male specimens of Africanus probably stood 4.5 feet tall and weighed around 90 pounds. Females would have been about 4 feet tall and weighed about 65 pounds. This would make Africanus in general smaller than Australopithecus afarensis. However, the brain volume of Africanus was slightly larger than afarensis, with a range between 420 and 500 cubic centimeters. It is largely in the skull of Australopithecus africanus that we can best see the differences between Africanus and the older afarensis. The slope of the face is more vertical, the brow ridges are reduced, and the cheekbones are more narrow. The teeth are more human-like, and the shape of the jaw is parabolic as in humans. Endocasts of the brain of Africanus show significant increases in the frontal and parietal lobes in comparison to a chimpanzee's brain. This increase in size foreshadows the changes to the brain that will continue to evolve in the genus Homo. In Australopithecus africanus, we find incremental changes that are inching along characteristics which will become more pronounced in the genus Homo, such as flattening of the face and an increase in brain size. Let's wrap up our examination of the genus Australopithecus with a look at one last species, Australopithecus sediba. On August 15, 2008, paleoanthropologist Lee Berger was doing fieldwork north of Johannesburg, South Africa on the Malapa Nature Reserve. His 9-year-old son Matthew was along on the trip. Matthew was exploring the area around the dig site. He came upon what he thought was a fossil bone and alerted his father. Lee Berger came to look and was stunned to see what he recognized as a hominin clavicle embedded in a rock. Upon turning over the rock, he discovered on the opposite side a mandible with several teeth. The fossils turned out to be a new species of Australopithecus, which was christened Australopithecus sediba. The specimen was a young male about 4 feet 2 inches in height. Further fieldwork by Lee Berger's research team in March of 2009 turned up a skull which belonged to the same specimen. The fossils of Australopithecus sediba were dated to about 1.95 million years in the past. Australopithecus sediba shows a mixture of characteristics that are both akin to Australopithecus and the genus Homo. Lee Berger and his research team interpreted the fossils of sediba as being transitional between Australopithecus and Homo. Other paleoanthropologists argued that sediba represented a late branch of Australopithecines that was coexisting with Homo habilis. Homo habilis had made an appearance on the African scene at least 300,000 years or more prior to sediba. As Australopithecus transitioned to Homo, where to draw the line between the two was blurred. To help clarify the classification issue, other experts in paleoanthropology such as Richard Leakey were advocating reclassifying Homo habilis to Australopithecus habilis. Leakey felt that because of its small size and primitive characteristics, Homo habilis was a better fit in the genus Australopithecus. The association of stone tools with Homo habilis had been one of the hallmarks that had heralded the advent of the genus Homo. The lines of classification seem to blur even more when we consider a fossil discovery made in 1996. Paleoanthropologists Tim White and Bahrain Asfal, working in the Middle Wash area of Ethiopia, discovered the fossil remains of a new species of Australopithecus which was christened Australopithecus gari. The most interesting aspect of this find was that it seemed to be associated with stone tools. The use of stone tools was thought to have arisen with the advent of the genus Homo and Homo habilis. The fossils of gari were dated to around 2.5 million years ago. This puts gari in the time range of the appearance of Homo habilis. So what was going on in the time span of roughly 2.5 million years to 2 million years ago? We have different species of Australopithecus coexisting with the early species of the genus Homo. In this time span, we would have found the Australopithecine species Africanus, Gari, and Sediba, not to mention the co-evolving robust Australopithecines, the genus Paranthropus, as well as at least one member of the genus Homo, Homo habilis. What we can gather out of this seeming chaos is that evolution is in and of itself a random and tumultuous process. It will never neatly bow to our nicely organized diagrams or simple linear models. The complexity of evolution will always appear a bit messy to the orderly human mind. Back in Chapter 3, we looked at DNA and the concept of organisms as expressions of a gene pool. Over many thousands of years, these gene pools diverge and evolve in different directions. This is what we see when we look back on the time span of 2.5 million to 2 million years in the past. Eventually, the gene pools represented by the Australopithecines and the genus Paranthropus ran their course. The gene pool represented by our own genus Homo continues to buoy us along on its tide as we move forward into the future. And if we were to look farther into that future than we dare imagine, advanced forms of space travel could lead to our own human gene pool becoming separated by vast stretches of space and time. Homo sapiens might begin to undergo speciation. 1 million or more years in the future, we may find Homo sapiens marsarensis or Homo sapiens centaurensis living and thriving far from Earth. But the future of Homo sapiens is a story yet to be written. In Chapter 8, we will continue our quest to discover who we are and where we came from with the help of paleoanthropology as we begin to look at our own genus, Homo. Homo sapiens. Who are we? Where do we come from? In Chapter 8, we will begin our look at our own genus Homo with the help of paleoanthropology. Let's begin with a general overview. This will help establish a roadmap for the journey ahead. As we begin our overview of the genus Homo, let's keep in mind that there is often debate among paleoanthropologists over fossil discoveries. Is a newly discovered hominin fossil a new species or just a variation of a known species? This will be a recurring issue as we move forward in our look at the genus Homo. As we noted in Chapter 7, where to draw the line across diverging gene pools is not an easy task. Let's begin. The earliest species assigned to the genus Homo is Homo habilis. The first fossil find designated Homo habilis was found in 1960 in Olduvai Gorge in Tanzania by Jonathan and Mary Leakey. The time range of Homo habilis is approximately 2.5 million to 1.4 million years in the past. Going down the timeline, we would next encounter Homo rudolfensis. The fossils of Rudolfensis were discovered in 1972 on the east side of Lake Turkana in Kenya by a research team led by Richard and Meave Leakey. The estimated age of Rudolfensis is 1.9 million years in the past. Next on our timeline, we encounter Homo ergaster. The designation of ergaster as a species is a point of debate among paleoanthropologists. There is a school of thought that ergaster is just a variation of Homo erectus. Others feel ergaster fossils vary enough from later fossils of erectus, especially those discovered outside of Africa, that it warrants ergaster being designated as separate species. The first fossil find designated Homo ergaster was made in 1971 in Kobe Ford near Lake Turkana in Kenya by members of Richard Leakey's research team. The fossil was first designated Homo habilis. In 1975, Colin Groves and Vratislav Mazik reassigned the fossil to a new species which they called Homo ergaster. The range of ergaster is estimated to be 1.9 to about 1.4 million years in the past. Next on our timeline, we encounter Homo georgicus. The fossil remains of Homo georgicus were discovered in 1991 by paleoanthropologist David Lord Kipanitsa in Dmanisi, Georgia. The fossils were first thought to belong to Homo ergaster. In 2002, the fossils were assigned to the new species Homo georgicus. The fossils of Homo georgicus were dated to about 1.8 million years in the past. This important find clearly demonstrates that members of the genus Homo had migrated out of Africa by 1.8 million years ago. Next on our timeline, we encounter Homo erectus. Homo erectus is thought to have been the first hominin ancestor to migrate into Asia. The first fossil remains of Homo erectus were found in 1891 by Dutch anatomist Eugene Du Bois in Indonesia at Trinil along the banks of the Solo River on the island of Java. Du Bois assigned his find to a new species he called Pithecanthropus erectus. The fossils were later reclassified to the species Homo erectus. The time range of Homo erectus is around 1.5 million years ago to as late as 70,000 years ago. Next on our timeline, we encounter Homo antecessor. The first fossils of Homo antecessor were found in 1994 at the Grandolina site at Sierra de Atapuerca in northern Spain by Eudal Carbonell and fellow researchers. The fossils of antecessor represent the oldest hominin fossils discovered in Europe. The range of antecessor is estimated to be 1.2 million years ago to around 780,000 years ago. Some paleoanthropologists believe that Homo antecessor should actually be classified with the next hominid ancestor on our timeline, Homo heidelbergensis. The first fossil of Homo heidelbergensis was discovered in 1907 in Mauer, Germany by Daniel Hartmann, a workman at a local sandpit. Mr. Hartmann gave the fossil jaw to Otto Schoetensack, who was a professor at the University of Heidelberg. Professor Schoetensack assigned the fossil to a species he named Homo heidelbergensis. The time range of heidelbergensis is about 700,000 years ago to as late as 200,000 years ago. Next on our timeline is Homo rhodesiensis. The first fossils of Homo rhodesiensis were found in 1921 by Swiss miner Tom Zwigler at the Broken Hill mine in what was then northern Rhodesia, but in the present day is Kabwe, Zambia. Due to the lack of proper scientific excavation of the fossils and subsequent destruction of the discovery site, dating is difficult. The estimated time range of rhodesiensis is 300,000 to 125,000 years in the past. Some paleoanthropologists classify the rhodesiensis fossil as being Homo heidelbergensis. Next on our timeline is Homo neanderthalensis. The first fossils designated Homo neanderthalensis were discovered in 1856 in a cave near Dusseldorf, Germany during mining operations by limestone quarry workers. The fossils were given to an amateur naturalist, Johann Karl Vollrath. Vollrath brought the fossils to Hermann Schaffhausen, a professor of anatomy at the University of Bonn. Schaffhausen and Vollrath made the discovery of the fossils public in 1857. In 1864, William King, a geologist teaching at Queen's College Galway in Galway, Ireland, suggested that the fossils be given the species name Homo neanderthalensis. The time range of neanderthalensis is about 300,000 years ago to around 30,000 years ago. Last and still standing on our timeline is our own species, Homo sapiens. The oldest known fossils of Homo sapiens were discovered in 1967 by Richard Leakey and members of his research team along the Omo River in the Kibish Formation in southern Ethiopia, approximately 100 miles north of the Kobe-4 fossil site. The fossils were initially dated to 130,000 years in the past. From 1999 to 2003, other research teams returned to the Kibish Formation to continue the fieldwork. Among the researchers was geologist Frank Brown of the University of Utah. Using advanced potassium-argon dating techniques, Frank Brown was able to more accurately date the Kibish fossil layer to 195,000 years in the past. The time range of Homo sapiens is around 200,000 years in the past to the present. Putting all of this together, we can create a general overview of the evolution and spread of the genus Homo. Using the fossil evidence we have covered in past chapters, we will create an epicenter of human evolution at Lake Turkana in northern Kenya. If we inscribe a circle around Lake Turkana with a radius of about 700 miles, we find ourselves encompassing a large area of the Great Rift Valley, which has borne witness to at least 6 million years of hominin evolution. From Auroran tugenensis in the Tugen Hills of Kenya to Ardipithecus in the Awash River Valley of Ethiopia, to finds of Australopithecus in Ethiopia, Kenya, and Tanzania, to the find of Homo habilis in the Olduvai Gorge in Tanzania, to the discoveries of Homo ergaster near Lake Turkana, right up to the discovery of the oldest known fossils of Homo sapiens in southern Ethiopia, there is no other area on Earth that offers such a rich and continuous hominin fossil record. If we were to pick a birthplace for humankind, this area would be a good bet. Let's now take a look at how the genus Homo left this homeland and began to spread across the Earth using fossil evidence as our guide. Looking at our map of fossil sites, let's add a handful of other sites which will help flesh out the timeline for the genus Homo. In Ethiopia, we can add a Homo ergaster site in the Bori Formation in the middle Awash River Valley. In Western Africa, we can add a Homo erectus site at Tianif in Algeria, as well as sites in Casablanca and Saleh in Morocco. In Southern Africa, we can add a Homo ergaster site at Zwartkrans in South Africa, which lies just about a kilometer from the Sterkfontein fossil site. Moving out of Africa, we can add a Homo erectus site at Ubaidiya in Israel. More Homo erectus sites can be added in Java at Mojokerto, Sangiran, and Nyangdong. Moving farther east into China, we can add Homo erectus sites at Yanmao, Lantian, Hexian, and Zhukoodian. Let's now make an attempt to establish a general timeline for the spread of the genus Homo out of Africa. The migration or movement out of Africa was probably incremental movement spread over thousands of years. A growing population and competition for resources may have caused groups of our ancestors to move into less populated areas where resources were more plentiful. With Lake Turkana as our center point, let's start our clock ticking around the 2 million year mark. Somewhere in this time frame of 2 million to around 1.8 million years ago, we would find Homo ergaster making an appearance in eastern Africa. Using the fossil site in Dmanisi as an early benchmark, we see that the genus Homo had moved north out of Africa by around 1.8 million years in the past. This gives us about a 200,000 year range for the spread of ergaster from Lake Turkana to Dmanisi. The walking distance from Lake Turkana to Dmanisi is about 3,000 miles or about 4,800 kilometers. Allowing for an annual expansion rate of just 1 mile a year, we see that it would take only about 3,000 years for our ancestors to have expanded their range into the regions around the Black Sea. At the same rate, it would have taken about 10,000 years for Homo erectus to expand into Java in Indonesia, where we also find fossil sites dated to about 1.8 million years ago. The sparse fossil record does little to provide a solid timeline for the spread of the genus Homo out of Africa. But we can speculate that from around 1.85 million years ago to around 1.75 million years ago, Homo erectus had left Africa. Our ancient ancestors had traveled more than 10,000 miles over a speculated range of 100,000 years. This works out to an expansion rate of about 528 feet per year. If we include the oldest date for the Atapuerca site in Spain of 1.2 million years ago, then it is possible some late variant of Homo erectus had moved into Europe by that date. By 1 million years ago to around 700,000 years ago, Homo erectus and its variants had spread across Africa into Asia and Europe. We have fossil sites in Western Africa and China that testify to the appearance of Homo erectus in these areas by 700,000 years in the past. Homo erectus had become the most widespread and successful hominin species of the ancient world. Yet for all the success of Homo erectus, the future of the genus Homo still lay in Africa. In Chapter 9, we will begin to unravel the mysteries of the genus Homo as we continue our quest to find out who we are and where we came from. Homo Sapiens. Who are we? Where do we come from? In Chapter 9, we will continue the quest we started back in Chapter 1. Homo habilis was thought to be the first representative of the genus Homo, making an appearance roughly 2.5 million years ago. Homo habilis is thought to have arisen out of the Australopithecines, especially as represented by the species Australopithecus gari. Around 1.8 million years ago, we would find the appearance of Homo erectus. Homo erectus in Africa is known as Homo ergaster. Somewhere in this time frame, we would find Homo georgicus appearing near the Black Sea in the present-day Republic of Georgia. Around 1.2 million years ago, we would find Homo antecessor appearing in what today is northern Spain. Homo antecessor is thought to be an early precursor of Homo heidelbergensis, who makes an appearance around 700,000 years ago. Homo heidelbergensis is found in Eurasia and Africa. Fossils of heidelbergensis have been found at numerous sites including Germany, France, Ethiopia, South Africa, Tanzania, and Indonesia. Homo heidelbergensis gave rise to Homo neanderthalensis and Homo sapiens. Homo neanderthalensis appeared around 300,000 years ago in Europe. Homo sapiens appeared around 200,000 years ago in Eastern Africa. Again, this is an oversimplification of a complex process, but it takes us where we want to go, and that is the 200,000 year mark in the appearance of Homo sapiens in Africa. Let's take a look at some of the most important fossil finds as relates to Homo sapiens. The earliest fossil finds of our own species Homo sapiens were found in Africa. The oldest known fossils of Homo sapiens are dated to around 195,000 years ago. These fossils were discovered in 1967 in the Kibish Formation along the Omo River in southern Ethiopia by a research team directed by Richard Leakey. Another important fossil find designated Homo sapiens adultu was discovered in 1997 at the Herto Buri site in the Middle Awash River Valley in northeastern Ethiopia by Tim White. The Homo sapiens adultu fossil was dated at 160,000 years in the past. Analysis of the fossils of Homo sapiens adultu found them to be transitional between older archaic humans and fully modern humans. Archaic human characteristics would be those exhibited by earlier members of the genus Homo, such as Heidelbergensis and Neanderthalensis. Characteristics which would differentiate archaic humans from anatomically modern humans would include a thicker skull, prominent brow ridges, and lack of a prominent chin. As evolution is a gradual process, one would expect to find transitional characteristics as the genus Homo evolved from archaic forms to anatomically modern humans. This is exactly what we see in the fossils of Homo sapiens adultu. In 1976, Dr. Mary Leakey's research team working in northern Tanzania made an important fossil find in the Nogolobo fossil beds at Litoli. The fossil find was of a Homo sapiens skull designated Litoli hominid 18 or LH18. The fossil was dated to 120,000 years in the past. The skull displays a mixture of archaic and modern Homo sapiens features. Another important site for Homo sapiens remains is the Klassies River caves located near the Klassies River in eastern Cape Province in South Africa. The site is dated across a span of 125,000 years ago to 70,000 years ago. Excavations at the site have presented evidence for early human behavior ranging from migratory habits to cannibalism. The Klassies River Cave site represents one of the oldest fossil sites of anatomically modern humans. It is also one of the oldest sites which shows the use of marine resources by humans. Another important human fossil find is the Hofmeyr skull dated around 36,000 years ago. The skull was found in 1952 near Hofmeyr, a small town in eastern Cape Province, South Africa. Recent analysis of the skull showed that it displayed features with a close affinity to the Cro-Magnon people who lived in Eurasia. This lends support to the out-of-Africa theory, which is based on genetic studies of human DNA. The out-of-Africa theory proposes that all modern humans are the descendants of a population of humans that originated in Africa. That population began migrating out of Africa 70,000 to 60,000 years ago. The Hofmeyr skull's close affinity with Cro-Magnon skulls found in Europe seems to point to a common population origin in support of the out-of-Africa theory. In our journey so far, we have depended on paleoanthropology to illuminate the nature of human evolution. The Homo sapiens fossil sites we have just reviewed seem to support the origin of Homo sapiens in Africa. We will now turn to genetics, and in particular evolutionary genetics, as we continue our quest to find out who we are and where we came from. Let's now take a closer look at the out-of-Africa theory with the help of evolutionary genetics. Evolutionary genetics is a synthesis of the science of genetics with Darwinian evolution. At the heart of this broad discipline is DNA. As we noted back in Chapter 3, DNA is the primary mechanism underlying evolution. It is literally the code of life. Over some several billion years of evolution, the original DNA gene pool has mutated and changed to populate the Earth with the breadth of biodiversity we see today, including our own species, Homo sapiens. Within our human DNA, we carry the history of our evolutionary past. Our evolutionary history is stored in genetic mutations which scientists refer to as genetic markers. Recent advances in DNA sequencing have allowed scientists to study these genetic markers in greater detail. By studying and comparing DNA sequences from numerous diverse human populations around the world, the scientists involved in evolutionary genetics have been able to create a general picture of the appearance and spread of modern Homo sapiens out of Africa into the rest of the world. Geneticists have been able to catalog a series of genetic markers that help in mapping the spread of humans out of Africa. Because genetic mutation is theorized to occur at regular intervals over time, scientists have also been able to provide time frames for the occurrence of these genetic markers or mutations. This has allowed scientists to trace the genetic line of modern human males to a theoretical most recent common ancestor who lived about 142,000 years ago in Africa. This ancient ancestor is popularly known as Y chromosomal Adam. Just as male lineages can be traced through the Y chromosome, matrilineal or female lineages can be traced through mitochondrial DNA, which is abbreviated mtDNA. All human cells contain organelles called mitochondria. Mitochondria are involved in the production of adenosine triphosphate or ATP. ATP is a chemical power source for our cells. Mitochondria contain their own DNA. Mitochondrial DNA is inherited solely through the lineage of the mother. Geneticists have been able to sequence the mitochondrial DNA and use the resulting information to trace the human female lines of genetic inheritance. Just as in the case of the Y chromosome DNA for the patrilineal line, mitochondrial DNA mutations or genetic markers have allowed scientists to trace our common ancestry back to our matrilineal most recent common ancestor, who lived around 200,000 years ago in eastern Africa. She is popularly known as mitochondrial Eve. The genetic placement of Y chromosomal Adam and mitochondrial Eve in eastern Africa between 200,000 years ago and 140,000 years ago is in accordance with the fossil evidence which finds the oldest Homo sapien fossils dated at 195,000 years ago in eastern Africa. Both paleoanthropological data and genetic data support the out-of-Africa theory for the origin of the modern human population. Let's now take a look at how scientists involved in evolutionary genetics have used genetic markers to map the spread of Homo sapiens out of Africa. One of the first things we want to do is define a term we will be using as we move forward. That term is haplogroup. A haplogroup can be thought of as an ancestral clan that shares a common ancestor. There are Y chromosome haplogroups for the patrilineal line and mitochondrial DNA haplogroups for the matrilineal line. These haplogroups are designated by their genetic markers. The genetic markers or mutations that define a haplogroup or clan are called single nucleotide polymorphisms, abbreviated to the acronym SNP, which is pronounced SNP. A single nucleotide polymorphism is a variation in the DNA sequence of an individual created when a single nucleotide in a section of the DNA sequence is altered or mutates. Back in Chapter 3, we noted that there are 4 nucleotides which encode for DNA: adenine, thymine, cytosine, and guanine. A single nucleotide polymorphism might occur when the nucleotide cytosine is replaced with the nucleotide thymine in a section of the DNA sequence of an individual. For example, if one individual had a DNA sequence in a given block that read A, T, T, C, C, T, A, T, C, G, and a second individual had a DNA sequence in the same block which read A, T, T, C, 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 A, T, C, G, this difference in the DNA sequence of the two individuals would represent a single nucleotide polymorphism or variation in the DNA sequence. These single nucleotide polymorphisms or SNPs are used to define haplogroups, or clades as they are sometimes called. In the modern human population, the most ancestral or base haplogroup of the patrilineal line is designated haplogroup A, Y DNA. Haplogroups are designated by the letters A through T in the Y chromosome line. The haplogroups are further subdivided through the addition of numbers and letters, example being the haplogroup R1b. The genetic mutations or SNPs that define haplogroup A would be found in the earliest descendants of Y chromosomal Adam. Haplogroup A is largely found in Africa. It is found in the highest modern frequencies among the Khoisan people, such as the San Bushmen. Genetically speaking, this makes the San Bushmen one of the oldest living representatives on the Homo Sapiens family tree. Let's take a look at the diagram of the evolutionary tree of the haplogroups that comprise the Y chromosome family tree. Farthest back in time, we would find haplogroup A in Africa represented today by the Khoisan people. We would also find haplogroup B represented by the Pygmies and the Hadzabe peoples in Africa. The CT haplogroup comprises the haplogroups or subclads C through T, which occur largely outside of Africa. Men in the CT haplogroup all have Y chromosomes with the M168 single nucleotide polymorphism or mutation. Haplogroups A and B, which are basically African, do not have the M168 mutation. The significance of the CT haplogroup and its M168 marker is that the CT haplogroup gave rise to all the male lines outside of Africa. The ancient ancestor of this line is sometimes called the Eurasian Adam, as it was his sons that migrated out of Africa to populate the rest of the world. The M168 mutation, or SNP M168, is thought to have arisen around 68,000 years ago in Africa, around the time the modern human population began migrating out of Africa. Genetics are derivative from parent to child. The Y chromosome passes from father to son down through time. Y chromosomal Adam appears 142,000 years ago. His sons eventually give rise to Eurasian Adam, who first displays the mutation M168, or the SNP M168, around 68,000 years ago. The sons of the Eurasian Adam begin the migration out of Africa to populate the rest of the world. The M168 mutation is strong genetic evidence that the modern human male population originated in Africa. Let's now look at the mitochondrial DNA evidence on the matrilineal side in support of the out-of-Africa theory. If we look at this diagram of the mitochondrial haplogroups, we can see that the oldest mitochondrial haplogroup is L. Mitochondrial haplogroups are designated using the letters A through Z, similar to the Y chromosome haplogroups. The mitochondrial haplogroups, however, are named in the order of discovery. They therefore don't line up chronologically in time. For example, the haplogroup of mitochondrial Eve is designated haplogroup L and is thought to have originated around 200,000 years ago in Africa, whereas the mitochondrial haplogroup A is largely found from Eastern Asia into the Americas. Mitochondrial haplogroup A is believed to have originated in Eastern Siberia roughly 40,000 years ago. One of the deepest ancestries among peoples living today of the mitochondrial haplogroup L would be the Khoisan people, such as the San Bushmen of Africa. An important subclad of the mitochondrial haplogroup L is the haplogroup L3. The mitochondrial haplogroup L3 is believed to have appeared in Eastern Africa roughly 90,000 years ago prior to the out-of-Africa migration. All mitochondrial haplogroups outside of Africa are derived from the L3 haplogroup, another indication of the origins of the modern human population in Africa in support of the out-of-Africa theory. No doubt the genetic aspect of the out-of-Africa theory can be somewhat complex. But the takeaway from all we have discussed is that the modern human population originated in Africa roughly 200,000 years ago. Around 70,000 to 60,000 years ago, a small group of that population began migrating out of Africa. It is thought that this migration started from the present-day country of Djibouti on the Horn of Africa and moved across the Bab el-Mandeb or Mandeb Strait into present-day Yemen. These modern human migrants spread along the coast of the Arabian Peninsula around to present-day India, reaching Australia roughly 50,000 years ago. Over some 60,000 years since our ancient ancestors first made the trip across the Bab el-Mandeb into the Arabian Peninsula, our species, Homo Sapiens, has spread across the face of the earth and begun to take our initial steps onto the neighboring bodies of the solar system, a spectacular achievement by any measurement.